Hey guys. Yeah, so today let's look at mesh shaders. So I have my whole framework ready and I load the GLTF file from uh, I'll load the GLTF file, I render and I already have the vertex buffers, everything set up. So when I started with mesh shader and I set up the pipeline and I got the same VBs, IBs which I know are correct, and then when I ran it, this made me laugh. I mean, it is like a deer. I can see the horns, I can see the face, I can see the legs, but it looks like a scribble. My daughter, when she grows up a little more, if I ask her a deer, maybe she would just scribble like this. And well, this is this is the output right now. So, setting up the mesh shader pipeline was much more simpler than ray tracing pipeline because it is not that different. I made a small slides on pictures on what to explain dispatch mesh. Anyway, so this is draw, very old, and we all know, and it's been there around for a very long time. So you set up the IA layout, and you set up the pipeline, you set up the rasterizer state, and then you call draw with these many number of indices or vertices or something, and then the vertex shader executes, transform the user's MVP matrix, and then goes to the rasterizer, and then the pixel shader output. So that's a traditional draw which has done a lot of good and even now it's widely used. And then we have this compute. So this is uh, the recently popular AI engines and all use a lot of compute shaders under the hood. But anyway, it's been there around for a while. You do post processing with it and you do something, and then you write it to the UAV, and it's a lot. It's been there around for a very long time, and games used a combination of dispatch and draws to render the frame. Now, well, both of them combined, they married, and then we get the advantages of compute, which is the flexibility, and the advantages of draw, which is a visual output, and which has enabled and all the advantages combined, and it has enabled Unreal Engine to make nanite meshes, which display extremely detailed models at real time because the compute shader allow you to do culling, frustum culling, LOD selection, and various other optimizations without it uh, uh, in general, it provides a lot more flexibility with the advantages of the visual output of the rasterizer. So, so coming back to this, so what do we need to write here? We need to this is an AS is an amplification shader, which is optional, which I'm not going to talk about it right now because my sample doesn't use it, and I still have to learn about it. But it's optional. It uses mesh shader, which is required because mesh shader is what reads the vertex buffers and the index buffers and then emits the triangles for the rasterizer to consume and for the pixel shader to display. Again, the rasterizer part is optional. If you want, you can write it directly to a UAV and then consume it later. So how does my pipeline look like? So, well, we saw the output, and this is a wireframe which renders this in wireframe mode. So this part is very familiar, traditional draw. This part is what is different. We have the AS and the amplification and the mesh shader, and then we have the root signature here. What is different here? Let's look at the shader because shader is a bit difficult. Uh, Not difficult. It's different, and you need to put on your compute shader hat and your rasterizer hat to to make a sense of this. So this is a familiar part. This is a pixel shader, and we just output the white color which we see on the screen. This is the new part. This is the mesh shader. It has all characteristics of a compute shader. We declare the local thread group size here, and then we use the GID and the TID to pick up what work we need to do, and finally we out and then sorry, and then this is our target. We need to use the vertex buffer, index buffer, uh, and fill up the indices and the vertices for what they call it as a meshlet. So you have so my idea is a huge mesh, and then each thread group, that is each whatever you define here, each thread group can output a maximum of 256 vertices and 256 indices, but there's an optimum size which game engine select as uh, per the GPU implementation. I think AMD would have one size, and then NVIDIA would have one optimal size. So, well, it's a bit of work. This is a bit of work. But let me take a pix capture and show what am I trying to do here. So let's dive into pix. I already have the capture, but I don't know which capture it is. Let's just say no, and then I think it's the same capture. Anyway, delete and then launch the process, and then next, and then launch pix. So let's take the output. Let's open the pix, start analysis, and then what am I trying to do? So this is our dispatch mesh. So let us see what are the bindings. So this is a mesh shader and this is a pixel shader. Pixel shader, very simple. We know we are just obtaining white, and then this is a mesh shader. So what are the bindings in the mesh shader? This is the index buffer and the vertex buffer. So what am let's let's have a representation of this. Let's say short, and so this is the index buffer, and let's have a representation of this. Okay, perfect. Flow through. These are the positions. So what am I trying to do in this mesh shader? I am reading the index buffer and the vertex buffer, and each thread outputs, and the thread group as a whole, the 64 threads which get launched in this one thread group should collectively output 64 primitives, 64 u in 3 indices. If you think about it, it is 192 indices and then 192 vertices. This is what I'm trying to do. This is not very optimal because we would like to eliminate overlapping vertices, but since it's a simple learning example, this is what I decided I would do, and maybe later optimize it in further sample applications, more advanced sample applications, which I plan to do. So okay, so these calculations. Okay, so this is the important part. Each thread group needs to tell how many vertices and how many triangles it is outputting, so that the compiler or the driver or the GPU can reserve that much space to store the data. So in my example right now, the way the code is right now, I am outputting 192 uh, 192 vertices and how many primitives? 64 primitives. Just give me 1 minute. Okay, sorry. So I am outputting 192 vertices, and actually it's 192, but the spec says how many primitives are you outputting. This 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 line could be triangles or lines. And for lines, it would be a u in 2. For triangles, it is u in 3. So that's why it says, so that's why I say that my topology is triangle, and I'm outputting the indices to represent 64 triangles. So I'm stressing it because it's anyway. I'm stressing it. So yeah, this this we have this part because it is not necessary. There's a lot of flexibility that it is not necessary that each thread needs to do some particular job, this particular job. No, if you want, you can output all this data on the first thread and mask all the other threads. So it's it's up to you how you write a shader, and it's up to you how you want to optimize. What I did in this example is each thread writes one uint 3 index, that is 3 indices and 3 vertices. So a total of 64 threads in this thread group would write 64 indices and 192 vertices. Okay. Now, the calculations which I do to access the index buffer and the vertex buffer is very similar to what I did in ray tracing. Even in ray tracing, we get a primitive index and we need to access the index buffer and the vertex buffer. So this part is very similar. So this part, what I'm doing is for this thread, which part of the index contains the data. So I calculate this, and then I calculate the vertex index position, the vertex index to write into this output, because each because of because say the first thread writes writes 0, 1, 2 vertices of 0, vertices of, okay, let's just say v vertices of v1, v2, v0, v1, v2, and it outputs try 0, the first thread. And how do I get which is the first thread? It is gid equal to 0 and gtid equal to 0. So based on the gtid varies from 0 to 63 and the gid varies from 0 to, or in the x dimension, 0 to 91, right? 0 to 63 and 0 to 91. So if you put all this together, we would be able to understand these computations. Okay, so if you go through picks, what am I doing? So the index buffer, the first thread works on these three elements, uh, these three, and it indices these three and writes it to the output. The second thread works on these three, 3, 4, 5, and even here 3, 4, 5, and then writes the output. But to index this, we need to access this, because this says element 0, element 1, element 2. It's not, this doesn't mean vertex 0, vertex 1, vertex 2. It's like vertex 0, vertex 1, vertex 2, vertex 1, vertex 3, vertex 2. So we need to access a vertex buffer through the index buffer. Okay, so that aside, so that I hope this gives an overview of what I'm doing, and this is MVP transformation matrix. We'll be playing around with that a little. I'll show you. Okay, so I captured the pics just for illustrative purposes right now, and as I showed you in okay, let's do a simple stepping through the mesh shader. That might help to understand a little more. So step through. So this is the global thread ID. The global thread ID meaning it varies from what is the global thread size. So I have 92. Let's open up the calculator. 92 is my dispatch size, and 64 is my local thread size. To 64. That is, my x dimension can vary from 0 to 5, 5, 8, 8, 8, 8, and this stays 0, 0 because I'm not using the y and z directions. For example, if I say 5, 8, 8, 8, 9, it say 5, 8, 8, 9. It says well, no invocations because there are no invocation records. And if I say 588, sorry, 5888 also is no invocation because it's zero based. So you get, and if I do 7, this is the this is, we are seeing the last invocation of the entire dispatch mesh. So let's see the first invocation, which would be a little easy uh, to correlate, right? So okay, so our mesh started, and then let's see what the first thread. So in out of 64, one out of the whole global 5888 threads, this is the first. This is the first thread. So what is the first thread, right? And yeah, this is unavailable problem. Okay, this unavailable problem is because the way shader debugging works is this when I'm stopping here, that doesn't mean that the GPU has actually stopped its execution. It doesn't work. It doesn't work how the CPU stepping works. So the GPU has run the shader, put a lot of instrumentation code in between, and collected all the data, and it is just allowing us. And when we step through, it's just fetching data what it has already collected from the GPU, and that's the reason I can even go back, I can go front. So it's just a visual thing. We already have in the back, the pics in the back, it has all the data. But anyway, so the unavailable thing is because compute shaders do a lot of optimization, and even if the shaders are not optimized, it's very difficult to get the data from the GPU because they reuse the registers, they duplicate the register. Uh, they reuse the registers and they do some constant folding thing, and also it's not possible to get, so we need to work with what all data which we have. But anyway, what 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 do we expect? We expect all all are zeros here, right? So all are zeros, and the index buffer should have let's try to expect what it has. It should have 0, 1 and 2 as its elements. It has index buffer. When I read the index data, I have 0, 0, 1 and 2, and if you predict the when we index 0, 1 and 2, we should get 0 0.2, 0 0.18, 0 0.19. So okay, yeah. So now the vertex data, I am accessing it now. Oh, okay. So I am yeah. So the vertex data, let's see, 0 0.2, 0 0.9, the x coordinates are 0, 0 0.2, the x coordinates are 0. 0.2, 0.18, that's what we expected, right? 0.2, 0.18, 0.19. So, well, I checked everything and everything is correct. And even for thread 1, what do we need to do? So, yeah, even for thread 1, if we step through, anyway, it's all going to be correct like what I expected. So what's going on here? So let us try to visualize the mesh a bit more. So I generated a color lookup table so that I know what each mesh is generating. So let's put the color lookup table here. Okay, and then let us write the. So this is the same as what you would do in a vertex shader. Send data to the pixel shader. In addition to position, I'm sending the colors, and let's do one more thing. The rasterizer state. Let's try to take off the fill mode to see full triangles, and so we should be seeing the color coding of the meshlets. Uh, okay, we are seeing all white. That is because okay. So in my pixel shade, I'm actually returning all white. So let's take this and say input dot color. Okay. So if I do this, then I should be seeing the color coding of what each thread group writes. So each color indicates what each thread group is kind of writing. I have 64, but I have a lot more meshes. So, hmm. So, okay, this doesn't give us much information either. It is as bad as before. But now what I would do is, let's say I will reduce the problem statement. So instead of this, I'm going to reduce to this, and then let's say in my mesh, okay, let's output 64 triangles. That should be 64 triangles. That should be good. So I should be seeing only one color because each thread group outputs a single color. So, okay, so well, what is this? So let's get to know the mesh better. Let's see what we need to expect. So for that, what I'll do is I will go to my hello world because this renders properly, and then in hello world, what do I do? I call render model. So in this render model, let's see, let us play with the triangles and see for 64 triangles, what do we do? So I'm going to show you what IMGUI, sorry, yeah. So here we're going to take help of IMGUI and then play around with the mesh. I have a bit of code, I'll explain it, let's explain it because since I have IMGUI integrated, we can do this. So what this does is this allows me to take the triangle count from the user. So this is a bit of IMGUI code where I can show you what's the output of this. Let's set that to hello world, and then so the purpose of this exercise is to know the mesh better. So I have all these controls. So there's a total triangle count of 3588. So let's say I want 0, and let's keep increasing. Okay. So this is the order of the meshes. Okay. So since the model is turning, uh, the the triangles are get curled. But I think at 90 degrees we see all the vertices. So let's go to the camera and let's stop at 90 degrees. I mean, let's keep it fixed at 90 degrees. Where is the camera? The camera.cpp. In camera.cpp is where we make the view projection matrix, and this is shared by all the samples. So I don't, so one change here. So let's keep it at 90 degrees. I think those are 90 degrees is orientation where the first meshes are drawn. Right. So when I say 0 and I keep increasing, so this is what, let me say 64. Okay, so this is what we should be getting at 64, first 64 primitives. But what are we getting in the mesh shader? So as I said, I'm sharing the camera, so we should see when this should stop at 90 degrees and give us so this is completely wrong. This is like totally wrong. But I went through the code and then I stepped everything and everything seems to be correct. So let's look closer with the mesh shader. Our task is each thread group needs to output this indices and these indices and these vertices. And it was only I just went for a walk and I started thinking about it. Then what are the so and then I got an idea, and then what I did is I said, okay, let's output instead of this instead of 64, let's output 6 triangles, which means the first 4. Right, so what do we see? The first two, and I'm seeing something like this, and then I said, okay, fine, let's do a little more. Let's do 12. uh, Wait, I think I did a little more. Let's do 24. Or, yeah. So, well, this triangle is totally unexpected. So, what is going on? So, I went back to the to this, and let's put a thread count of 1. So what is our task? Our task is to segregate this into meshlets. Is to segregate this into meshlets. So if you see the first one, what am I doing? So the first one would output tries of 1 and vertices of 3, 4, 5. So as I step through the code, vertex index data, so 3, 4, 5. I'm outputting at vertex in indices, vertex indices 3, 4, 5, and I'm outputting 1, 3, 2 index. This is like, if you think about it, this is clearly wrong, because my assumption in this shader is there's a 1-1 mapping between the index and the vertices. So this I'm writing to the index 3, 4, 5, but I'm indexing the vertices 1, 2, 1, 3, and 2, which is like, which is wrong. And this took me a while to figure out, because the first time I'm writing a mesh shader, and we need to wrap our head around this. So um, because we are outputting a meshlet, and the vertices and the indices should index the vertices in the meshlet in the order in which they are written in the meshlet, not the original index buffer. So it so this was a very simple fix. So I am outputting, this is a vertex index, and this index I used to access an index into the vertex buffer, right? So this is not the data which I should write. I should write the vertex index here, right? I should write the vertex index here. Then I would be in then my index buffer would index into these vertices. Well, do you think it's fixed? Let's see. Let's increase the count to 64. And this seems to be working beautifully. And then let's go to the mesh shader and say, okay, let's do 64. I mean, more meshes. I need to calculate what should be the dispatch mesh size. I, that is yet to do. And here we are. Huh, that is a job well done. So let's go back to the camera, and then let's undo these changes, and let's run it again. And here we are, we have the data. So let's also try to texture it properly. Okay, so to texture it properly, all we need to do is, use the same code as my do I have this? No. So, well, I can write it, but I'm lazy. So let's go to VSPS, and then let's take this, and let's copy this code, just that sample and then sample. And not that simple. We have a little bit more work to do. Now, if you see, this is, I think the register is okay. Okay, the register is correct because I would be using T0 to access the texture and T1 and T2 to access the structured buffers, and I already have the in the root signature I'm already creating. Yeah, this is I mean, I always found root signature creation very bulky, so I figured out a way to make it a bit simple. So root parameter index 0 we have the CBV, root parameter index 1 we have a descriptor table with 3 SRVs, no UAVs, no CBVs, and so I am binding 1 and 2 here. So let's be a bit lazy, go back to the hello world, and then pick I need to, okay, all I need to do is it 0 is there, just do to descriptor table. I already found the root descriptor table. Oh, then I think we are all set because yeah, we're all set because I am already set finding the root descriptor table with at parameter index 1, and it already has my SRV ranges. It already has my SRV. So I think we should all be set then. Okay. What is this? Okay. Sorry. So, well, this is VS output, and I think I have text code 0. No, I don't have text code 0. I have UV here. Oh, okay, okay, wait, there's one more remaining. Ah, I think I know what is missing. So that's what I was thinking. It should not be, it can't be this simple. So let's just say vertices of vertex index of x dot uv equal to, what is it? It should be a pass through because the rasterizer interpolates it for us. So that's the thing. Here we have bound only position VB. Now I need to bind my so we need, this is the thing with this with rasterizer, we bind everything as an input layout. So now what I need to do is I need one more SRV for to read my UVs, right? And let us, okay, again shortcut with ray tracing. So in ray tracing I bind my UVs. Yeah, ray tracing I bind my UVs. So let's go to ray tracing and let's pick up this bit of code where I bind my UV buffer. So this is the IB buffer which we already bound. This is the UV buffer. Okay, so where we getting create this UV buffer resources here. UV buffer view. So let's copy this piece of code. So gain from the model, get the this, get this. Let's create the UVs. Let's the UVs here, and be surprised if this kind of works, but let's see. So here I'm binding the index buffer, vertex buffer, and this would be the UV buffer. Now how does the whole pipelining work? So this is the descriptor index at one at the index. So I have, as you can see, we have we have four, right? We have four here. So at 0 we have the texture. At 1, at 1, and that's SRV range. So 0, we have the texture. Uh, where am I binding the texture? That's that's a good question, right? When am I binding the texture? Because I don't. Okay, let's see. We should bind the texture also first. Anyway, let's get the UVs up and ready, and okay, 1, 2, and at the third I would bind the UV buffer. So then what I need from, let's go to ray tracing, and because I don't want to make any mistake now, let's take the UV buffer. Okay, we need to change a bit because T2 is already used for T2 is already used, so T1, T2, T3. So UV buffer. So technically what we should do is we have the UV buffer here. So we need to do vertices of UV equal to uh, UV VB buffer, right? Why is it not UV VB buffer? Let's see, let's do this. I mean, seriously, I'm doing this for the first time, so I hope I'll complete this within this tutorial time. So UVVB buffer of, which it would be the same way I index. I get the vertex data. So position VB index. So I need to do the index data dot x and it's dot UV, right? So we should get the float. So since it just passed through, I can just do this, right? So what is this of dot UV, sorry, dot UV equal to, and to get the index data and pass it on here. So this should be all right? Because this is T3 and I'm binding this as T1, T2, T3. We should read the UV buffers properly, right? So let's see what's the output. I think all the plumbing should have been set up properly by the app. No. So, oh, right. Okay. So I need to go back to, because we added one more SRV, so I need to go back to my mesh.h and request for 3 SRVs. Not 3, I should say create 4. Okay, I think all the plumbing should be correct now. I'm requesting 4 SRVs and we are getting something. Let's go to pics and see if our plumbing is correct. Okay, no. Launch process, the mesh shader, next, and launch. So what is happening? Well, this is a weird output, but okay, and then the pipeline state, dispatch mesh, start at analysis. So yeah, so hmm, so in the pixel shader, we do see that we have bound the texture, and all the plumbing seems to be correct. I think I know where what is going wrong. So when we see the shader, okay, this is T0 is correct, and this is amplitude UV, and what are we sending the UVs as? The UV buffer equal to UV VB. Oh, we are setting only. Okay, we are setting only. So we are setting only one UV, only for one triangle. So the interpolations are all going wrong. So see, so this is what the first vertex, the second vertex. and there's the third vertex, right? So this is the first index, x, y, and z. So now I think it should work. And yes, we have our deer in the mesh shader. So one doubt which I had when I was doing all this is where do I set this? Where do I set this? So what is? And I was thinking while doing this. So we have this load GLTF, which I still need to refactor a bit. But for now, if we go through load GLTF, I am loading materials, and while I'm loading the material itself, this is, I know this is very simplified, and I need to, I'm putting everything here, GLTF loader, and yeah, now I have all my pipelines working, so I'll work on this. So anyway, when I encounter a material, I'm just creating a texture 2D, I'm extracting the data, I'm creating a texture 2D, and I'm creating the descriptor at index 0. So this is a bit of a well-defined layout which I have, which I wanted to create for all the sample apps to follow, so that it is very easy. Okay, so well, this is what we have right now, and the mesh shader displays. We can do a bit of interesting stuff here because I have a color and a texture, right? So let's see, this is a sample color. So we have a float 4. Let's do a float 4 only. Float 4 so that we can 4 f float 4 meshlet color equal to dot color, and let us see if we can um, kind of multiply, right? SAMPLET sampled color into 0. Let's take a weightage of 0.5 for both. Plus SHLET color dot color. That's implicit truncation. Why is that implicit truncation? Sample color. Let's see. Let's fix that. Oh, okay. Meshlet color. Okay, and then I don't need to do this, right? But I can just do this. Sample color into meshlet color. So let's see. Sorry, I forgot 0.5 here. Because to 0, let's say 0.3 and 0.7 at the weights like this. So mishlet color is taking a lot of weight. So let's say 9, and sample color is 9, and mishlet color is 1. Yeah, the mishlet color is vibrant, so it's just overwhelming. So yeah, so this is a cool effect. We can see, this is a mishlet colors, and we can kind of know. Okay, not as good as I wanted, but I think we can play with the weights to get what I want. Good job. Thanks guys. That's it for now.